We're now on to the Chapter 7 review lesson, and in this video I'll be going over some old provincial exams related to Math 12 and the probability chapter. So let's get started. Question number 1. It is known that 22% of households have dogs as pets and 13% have cats. If 3% have both, what percent have neither? Alright, so for this question we need to set up a Venn diagram with two circles. So let's do that. Here's my Venn diagram. The blue circle will represent dogs and the red circle will represent cats. Now the first thing I'm going to do is I'm going to record this 3% here. So 3% have both, so that would be this middle region right here. And then after that I can find the percentage of dogs as well as the percentage of cats. The percentage of dogs will be 19%. So simply you just take the 22% and minus 3 and that will give you 19%. And 19 plus 3 will also give you 22% of the households that have dogs. And for cats, that would be 10%. That's simply going to be the 13 minus the 3 and that will give me 10% for cats only. Now I want to find the percent of neither, which is the percent in the outside region. So simply I take 100% and subtract the percentages above. So the percent of neither would be 100% minus the 19 plus the 3 plus the 10, and that will give me the percentage remaining in the white region. And that's going to be 68%, which is going to be option D. So 68% of the people have neither pets. Next question. A card is drawn from a standard deck of 52 cards, then replaced. In 20 draws of this type, what is the probability that a red card will be drawn exactly 12 times? Okay, so this is going to be one of those binomial theorem questions. So it's a binomial expansion because there are only two outcomes, red and black. So the probability of red will be 50% because in a standard deck of 52 cards, 26 of the cards are red and 26 of the cards are black, so the probability of being red would be 50%, and the probability of being a black card is also 50%, and 50% plus 50% equals to 100%, which is a condition for the binomial expansion problems. Alright, so since each card is replaced, each draw will be an independent event. So the probability of 12 red cards when we're picking, when we have 20 draws and we want exactly 12, that's going to be 20 choose 12 times the probability of having a red card, and that's going to be raised to the power of 12. And then for the second probability, that would be 50%. The probability of being a black card is 50%, and this 8 is simply going to be the 20 minus the value of r, so 20 minus 12 will give you 8. And once you go to your calculator and once you compute this, this will give you a probability of 0.1201, which is going to be option number C. Next question. Two fair six-sided dice are rolled and the face values showing are added. What is the probability that the sum of the face values is at least 9? Okay, so if we have a situation with two dice, it's probably best to draw the chart. So let's create a dice chart. So this diagram right here shows you the total number of outcomes when you're rolling two dice. So this is dice number 1 and dice number 2. So for dice number 1, you have 6 different outcomes, and for dice number 2, you also have 6 different outcomes. And this 1 here is the result of having 1 from your first dice and 1 on your second dice. So 1 plus 1 would give you a sum of 2. I want to look for the sums where the face value is at least 9. Okay, so let's find the values where we have a sum of at least 9. So let's circle the ones that have at least 9, and that's going to be this situation right here, 6 and 3. 6 plus 3 is 9. 5 plus 4 is 9, 4 plus 5 is 9, and 3 plus 6 is also 9. And then you have all these other outcomes in here as well. This is 10, 10, 10. Those are at least 9. Those are 11, 11, and 12. Those are all at least 9. Alright, so 10 out of the 36 cases have at least a sum of 9. So the probability of being at least the probability of having a face value greater than 9, greater or equal to 9, is simply going to be 10 divided by 36. And when you simplify that, that's going to be 5 over 18, and that's going to give you option B for this problem. Let's move on to the next problem now. A rock concert is attended by 1,300 students, of whom 760 are girls and 540 are boys. If 4 of these students are randomly chosen to receive backstage passes, what is the probability that at most 3 of the chosen students will be boys? Alright, so in this problem we have 540 boys and 760 girls. Only 4 of these students are picked to go backstage, and we want the probability that at most 3 of the chosen students will be boys. Okay, so when we're looking at one of these questions where we have at most something, so in this case at most 3 boys, we'll have several cases to consider. We can consider 0 boys, 1 boy, 2 boys, or 3 boys. This would represent all the different scenarios where at most 3 of the boys will be picked. Now, if we find the probability for 0 boys, 1 boy, 2 boys, and 3 boys, we actually have to calculate 4 different situations. A faster way to do this problem is to look at the complement. So the complement will be essentially having all 4 boys. So if we want at most 3 boys, I could calculate the probability of getting all 4 boys and doing 1 minus all 4 boys, and that would also give me the probability of having at most 3 boys. Alright, so we're gonna use the complementary method here, and that's simply going to be 1 minus the probability of having all 4 boys. And if we use this method, then we have exactly 540 boys, so 540 boys, and I want to choose 4 of them, so we want at most 4, and then I'm going to divide that by the probability of getting the total number of different hands here, which would be 1,300 students. Choose 4 because we only want 4 of these students picked. And if I go to my calculator here, this would simply be 0.9704, which is going to be option number D. Alright, let's move on to the next problem. For this problem, I have 10 discs numbered 0 to 9, and they're placed in a box. 2 discs are randomly removed from the box without replacement. Determine the probability that one disc will have the digit 5 written on it and the other disc will have the digit 6 written on it. Okay, so since for this problem we have without replacement, so this is a situation where the events are dependent. So a good way to solve this problem is by creating a tree diagram. So for the first choice, we could actually have a 5 or a 6, and then the other choice here would be all the other discs. And for the first choice, we could have a 5 or a 6 because the final outcome that we want to have is we want to have the probability that one disc will have the digit 5 and the other disc will have a digit 6 written on it. So it doesn't matter if I get a 5 first or a 6 first, as long as I have the digits 5 and 6 at the very end, then that would also satisfy this condition. So for your first outcome, you can actually have a 5 or a 6. Now when you go into the box again and you pick out another disc, the probability of getting a 5 or a 6 will be 2 out of 10 because from 0 to 9 that's 10 discs, and 5 and 6 will represent 2 different outcomes. And this probability over here will simply be, well, it's not important, but anyways, moving on here, if I pick a 5 here, for example, then that means there would be 9 discs left here and only 1 disc remaining because I want maybe the 6th disc, so this will be probably a 1 over 9. And hopefully that makes sense because if I originally have 10 discs and if I remove 1 disc already, then I'm down to 9. If I picked a 5 here, for example, then that 5 is originally gone from the 2, and then I would just have 1 remaining outcome left for the 6. So I would just follow this branch right down here. So the probability of getting a 5 then a 6 will be 2 out of 10 times 1 over 9 according to this diagram, and the probability of that would be 1 over 45. So the option is A. So I have a 1 in 45 chance of getting a 5 and a 6 after going into the box and picking out 2 random discs. All right, let's move on. For this problem, I have 2 events. Event A, a fair coin is tossed and shows tails. Event B, a fair 6-sided die is rolled and shows a number greater than 2. Determine the probability of A and B. All right, so for this question, you should recognize that the 2 events are independent because event A will not affect event B. So if we have 2 independent events, the probability of A and B is simply going to be the probability of A times the probability of B, and that's going to be 1/2 times 4 over 6. So if you flip a coin and if you want a tail, then the probability of getting a tail is 1/2. And for a 6-sided dice, if you want a number greater than 2, well, you're going to have 3, 4, 5, and 6, which are 4 different choices, so 4 out of 6. So that will give you a probability of 1/3, which is option number A. All right, next problem. For this question, I have a Venn diagram. The diagram below represents a sample space of 11 equally likely outcomes. Determine the probability of not A. Okay, so not A. So 6 out of the 11 dots are not in circle A. So those 6 dots are going to be 1, 2, 3, 4, 5, 6. And we have 11 dots total, so the probability of not A is simply going to be 6 out of 11, and that's going to be option number C, 6 out of 11. All right, so that problem was pretty quick. Let's move on to the next one. In this next problem, I have 2 hockey players, Tom and Jerry, and each of them will shoot a penalty shot. Tom has a 50% chance of scoring the goal, and Jerry has a 2/5 chance of scoring a goal. Assuming independence, that meaning that if Tom has no effect on Jerry if he's going to score a goal. That's what independence means. What is the probability that at least one of them will score the goal? Okay, so for this question, we need to kind of break down the different cases. There are 4 possible cases. The first case is Tom scores and Jerry scores. So if both of them score, then that would satisfy this condition where at least one of them will score the goal. The second case is Tom misses and Jerry scores. So in this second case, we have at least 1 goal scorer, so this is good. The third outcome is Tom scores, but Jerry misses. And this would also have at least 1 goal scorer. And the fourth outcome is when Tom misses and Jerry misses. So this fourth outcome would not satisfy the condition in this problem. Okay, so let's calculate the individual properties, 1, 2, and 3, and then we'll add them together. All right, so at least one of them will score. We'll include cases 1, 2, and 3. So let's calculate the probability for 1, 2, and 3, and then like I said, we just need to add them together, and that would give us our final answer. So if Tom scores and Jerry scores, that probability would be 1/2 times 2/5. And we can multiply these 2 individual probabilities because it says assuming independence, and that's going to give you 1/5. Tom misses and Jerry scores, that's going to be 1/2 times 2/5. So if Tom scores a goal, the probability of that happening is 1/2. Then the probability of him missing will also be 1/2. So 1/2 plus 1/2 would give you 100%. And the 2/5, that's just Jerry's probability of scoring a goal, and that will give you 1/5 when you multiply those 2 numbers together. The third case is Tom scores and Jerry misses. So Tom scores, that's a probability of 1/2, and if Jerry misses, that will be 3 over 5. Okay, so 3 over 5 plus 2 over 5, that will give you 100%. So the probability of Jerry missing is 3 over 5, and that will give you a probability of 3 divided by 10. And here's the calculation for the fourth case, but this case is actually not important. So the probability of at least one scorer, that's going to be 1/5 plus 1/5 plus 3/10. 3 divided by 10, which is these three cases. And that'll give you a probability of 7/10, which is going to be option number A. All right, next problem. For this problem, a 3-card hand is dealt from a standard deck of 52 cards. So we're drawing 3 cards from 52. What is the probability that the hand will contain exactly 1 queen? Okay, so there are 4 queens and 48 other cards. And from the queens, I want exactly 1 of them. So we can break this up into 2 categories. So the probability of 1 queen will be 4 choose 1, because I have 4 queens and I want exactly 1 of them, and that means I have 48 other cases or 48 other cards, and from the 48 then I will choose 2 because I have a 3-card hand. One of those cards will definitely be the queen and the other 2 cards will be the other choices. So 48 other cards, 48 choose 2. We multiply them across and divide by the total number of outcomes. We have 52 cards in a deck, and once again we're choosing 3, a 3-card hand. We go to our calculator and we get 0.204070, which will be option number B. All right, next problem. For this next problem, I have a spinner. If the spinner is spun 7 times, determine the probability that it will stop on either section A or B at least 5 times. Okay, so this problem might be a little long here. The probability of getting an A or a B is 2/3, and hopefully you can see that in this diagram here because I have 3 different outcomes, 1, 2, and 3. And if I want to get an A or a B, that would represent 2 outcomes, so that's going to be 2 out of the 3. And getting at least 5 times will include the cases of 5, 6, and 7 times. All right, so if I want to get A or B at least 5 times, I need to consider the probabilities of getting 5 of them, 6 of them, and 7 of them. All right, so the probability of getting an A or a B 5 times, well, this is going to be using the binomial theorem here because we have 2 outcomes, getting an A or a B, or not getting an A or a B. So the probability of 5 times would be 7 choose 5 because I'm spinning the wheel 7 times and I want at least 5 of getting A or B. The probability of getting an A or a B is 2 out of 3 and I want 5 of them. And the probability of not getting an A or a B will be 1/3. And this 2 right here is simply going to be the 7 minus the 5, which is 2, and I want 5 here, which is the R value there. I go to my calculator, calculate this out, and I get 0.30727. Now that's the probability of getting that's the probability of getting A or B 5 times. Then I also need to calculate this for 6 times and 7 times, and then add them all together. So the probability of getting an A or a B is 6 times. Well, that's going to be 7 choose 6 times 2/3 to the power 6 times 1/3 to the power 1. I go to my calculator, and that's going to be 0.20484. And then finally, I calculate the probability. And then I need to calculate the probability of getting an A or a B for the 7th time, which will be 7 choose 7 times 2/3 to the power 7 times 1/3 to the power of 0, which will just be 1. And that's going to be 0.05852. And then when you add all of these individual probabilities, that gives you the probability of being at least 5 times. And that's going to be 0.5706, and that's going to be option number D. All right, next problem. For this problem, I have a 7-card hand. And so a 7-card hand is dealt from a standard deck of 52 cards. What is the probability that the hand will contain 5 black cards and 2 red cards? Okay, so for this problem, we can use the bucket method because there are 2 categories. So let's set up our bucket right here. I have red and black. I have 26 red cards and I have 26 black cards. From the red cards, I want 2 of them, and for the black cards, I want 5 of them, and 2 plus 5 will give me the 7 cards that I'm picking from the deck. So the total number of desired hands would be 26 choose 2 times 26 choose 5, and then I will divide that by the total number of outcomes, which would be 52 cards choose 7. And then I go to my calculator, and I would get 0.15979. All right, so let's move on to the next problem because this answer is C. 2 fair 6-sided die are rolled and the face values are added. The probability of obtaining an odd number greater than 8 is... Okay, so we have a 6-sided dice. We have 2 of them. So the best thing to do for one of these dice problems is to make a chart and find the total number of outcomes. So once again, let's create a dice chart. And here's my chart right here, similar to one of my previous problems. And we want to find the outcomes where the face values are added and the sum will be greater than 8. So let's circle the situations where we have a sum greater than 8. So 6 plus 3 is greater than 8. This is greater than 8, this is greater than 8, and this is greater than 8. This is greater than 8, that's greater than 8. So basically, for this kind of problem, 6 out of the 36 cases have an odd sum greater than 8. Now, we got to be very careful here because the question states the probability of obtaining an odd number greater than 8. So even though 6 plus 4, that has a sum of 10, which is greater than 8, 6 plus 4 being 10, 10 is not an odd number. So I can't include this, I can't include that, and I can't include this because these sums have an odd number. And 6 plus 6 will give you 12. 12 is greater than 8, but once again, 12 is not an odd number, so we don't include this. So 6 out of the 36 cases have an odd sum greater than 8. So that's going to be 6 out of 36, and if I simplify that, that's going to be 1 over 6, and that will be option A. All right, next problem. A jar contains 3 chocolate chip cookies and X oatmeal cookies. 2 cookies are pulled from the jar without replacement. An expression that represents the probability of one cookie is chocolate chip and the next cookie is oatmeal is. Okay, so for this problem, I need a mathematical expression that represents a chocolate chip cookie, and the next cookie will be oatmeal. Okay, so the number of chocolate chip cookies is 3 chocolate chip cookies, and the number of oatmeal cookies would be X. We have X oatmeal cookies. That means the total number of cookies would be 3 plus X, which is X plus 3. And then we can use a tree diagram to get a chocolate chip cookie first and then an oatmeal cookie. So we can simply draw a tree diagram here. So this would be a chocolate chip cookie and this would be an oatmeal cookie. Now the probability of getting a chocolate chip cookie would be 3 divided by the total number of cookies, which is X plus 3. And I don't really care about the oatmeal side because I want a chocolate chip cookie first. And then for my second choice, I have a chocolate chip cookie or an oatmeal cookie. And for my oatmeal cookie, that would simply be X because I have X number of oatmeal cookies. And that's going to be divided by the total number of cookies, which will now be X plus 2, because if I picked a chocolate chip cookie over here, then that means I have 1 less cookie left for my second choices here. So this would be X plus 2. So once again, this 2 comes from minusing 1 from the denominator here because we have reduced the number of total cookies from X plus 3 to X plus 2. And then we simply just multiply these 2 expressions. And so the probability of picking a chocolate chip cookie first and then getting an oatmeal cookie, that's going to be 3 divided by X plus 3 times X divided by X plus 2. And that's going to be option number B. All right, next question. For the next problem, 3 cards are pulled from a deck of 52 cards. The probability of obtaining at least 1 club is, So I want to find the expression that would give me the situation of getting at least one club. So let's take a look here. If we have at least one club, that will include the cases with one club, two clubs, and three clubs. Now, another way to solve these problems is to look at the complement of this event, and that would be not getting any clubs. So if we want at least one club, the complement of that would be kind of like not getting any clubs. So let's find the probability of getting no clubs, and then we'll just do 1 minus that answer, and hopefully we'll get one of these answers here. Alright, so what's the probability of getting no clubs? Well, I have 13 clubs, and I'll choose 0 of them because, there's 13 clubs, and I want 0 of them, and that will give me no clubs. And then if I ignore all the clubs, that means I have 39 different cards in the deck. Remember, 39 plus 13, that will give you the standard 52 cards in the deck. And from the 39 other cards, I want to choose 3 of them because 3 cards are pulled from the deck. And then I'll divide that by the total number of possible outcomes, which is 52 cards in the deck, and I'm choosing 3 of them. So this is the probability of not getting any clubs. And then what I want to do next is I just need to subtract the complement from 1 to get the probability of getting at least one club. So the probability of getting at least one club will be 1 minus the complement, which is 1 minus probability of no clubs, and that's going to be 1 minus 39, choose 3, divided by 52, choose 3, and that's going to be option number D. Alright, next problem. For the next problem, I have 3 different DVDs and their corresponding DVD cases, and they're put on a shelf. If a young child puts the DVDs in the cases at random, we want to find the probability of correctly matching all DVDs with their cases. Okay, so let's look at the DVDs first. We need to find the number of ways to arrange the DVDs in their cases, and the number of ways to arrange 3 different DVDs, that will be 3 factorial. So 3 times 2 times 1 will be 6, which is 3 factorial. So there are 6 different ways to arrange the 3 different DVDs. And out of those 6 possible outcomes, only one of them would be correct in terms of matching them in their correct DVD cases. So the probability of matching all the DVDs in their proper cases is essentially going to be one of the outcomes from this total number of 6 outcomes. So that would be 1 divided by 3 factorial, which is option number A. Alright, next problem. For the next problem, I have a playoff series. The probability that Team A wins over Team B is 3 over 5. And the probability that Team C wins over Team D is 4 over 7. If the probabilities are independent, the probability that Team A wins and Team C loses is... Alright, so for this problem, they're basically just testing you whether you understand the concept of probabilities being independent. And when we have an independent situation, we just multiply the individual properties together. So the 2 events are independent, and basically we're being asked to calculate the probability of A winning and the probability of C losing, which is the same thing as probability of A times the probability of not C. So the probability of A winning is going to be 3 over 5, and the probability of C losing, well, that's going to be 3 over 7, because the probability of C winning is 4 out of 7, so the probability of C losing has to be 3 over 7. And we're simply going to multiply those 2 individual properties, and we get 9 out of 35, which is option number A. Alright, next problem. For the next problem, I have a 5-digit PIN number, and that can begin with any digit except 0, and the remaining digits have no restriction. If repeated digits are allowed, the probability of the PIN code beginning with a 7 and ending with an 8 is... Now for this problem, there is a small mistake. I don't have a 5-digit PIN number. Basically, I have the problem should state a 4-digit PIN number. Okay, so before I solve this problem, I just want to correct a small little mistake here. It's a 4-digit PIN number, can begin with any digit. Alright, so if I have a 4-digit PIN number, the first number has to be a 7 and it has to end with an 8. So let's find all the different combinations to get the 7 first and ending with an 8. And so that's going to be 1 times 10 times 10 times 1. Now, I have a 1 here because this has to be a 7. So for the first digit here, I can only have a 7 there, so I have one possible outcome. And then says the remaining digits have no restriction. So for the second and third digits, I have no restriction, so I have 10 possible outcomes for the second digit and 10 possible digits for the third digit. And finally, the last number must be an 8, so I only have one choice for the last number. And once again, this problem there was a mistake in this problem. It should have been a 4-digit PIN number. So if I have a 4-digit PIN number, then I have 4 choices, 1, 2, 3, 4. All right, so this would give you the total number of desired outcomes, and then we need to calculate the total number of outcomes, and then I just take this expression and divide it by this expression, and that would give me the probability. So the total number of outcomes essentially going to be 9 times 10 times 10 times 10. The reason why I have a 9 here is because it states in the question that a 4-digit PIN number can begin with any digit except 0. So the first digit cannot begin with a 0. So if I remove 0 from here, I have 9 possible choices for the first digit. And then for the second, third, and fourth, I have no restrictions, so I have 10 possible choices for the second, third, and fourth digits. So basically, I just take this expression here and divide by that expression, and I'll get 1 over 90, which is going to be option number D. So once again, there was a small mistake in this problem. This 5-digit is wrong. It should be a 4-digit PIN number. All right, let's move on. For the next problem, 2 cards are drawn without replacement from a deck of 52 cards. The probability of the first card being a red face card and the second card being a club is, well, I have without replacement, so that means we are dealing with a dependent situation. So for dependent problems, we should start off by drawing a tree diagram. And to start my tree diagram, I will have a red and a face card, and I'll have not a red and a face card. So for this problem, the first card must be a red face card. So the probability of getting a red face card is going to be 6 out of 52. There are 52 total cards in the deck. And for the 6, well, basically you have 12 face cards, but only 6 of them are red. So the probability of being red and being a face card is 6 out of 52. All right, and the probability of not being red and a face card is 46 out of 52. And this plus this will give you 100%. All right, now the second card has to be a club. So for my second case, I should have a club and a not a club. And the probability of getting a club, well, I have 13 clubs and I only have 51 cards left in the deck because this is without replacement, meaning I don't put the card back into the deck. So if I have 52 to begin with, and if I lose 1 card, I should be down to 51. So the probability of being a red face card and a club, well, I just simply multiply this branch right here, and that's simply going to be 6 out of 52 times 13 out of 51, giving me a total of 1 out of 34. That will be option number A.